example number 1. So right away, I can tell that this is going to be an integrated rate law problem. Not only did they give me like natural log numbers and reciprocal numbers, but you'll notice that this data table looks quite different from what we saw with differential rate laws. There is no experiment 1, experiment 2, experiment 3. Instead, I have a column of time and a column for concentration. Okay, that's what I mean when they say, hey, I'm giving you time data with the concentration data. And what they're doing in this experiment is they're starting the clock, they're starting the reaction, and they're monitoring the concentration of the hydrogen peroxide over time and seeing how it's changing. Okay, they're not changing the starting concentration of the hydrogen peroxide. There is no math way, there is no table logic for these types of problems. The only way we can do this is through the graph. Okay, so I already did the graph for you. And so let's take a look here. If I plot concentration on the y-axis, time on the x-axis, I get this curve. Is it straight? No, not straight. This is not a straight line. Okay, it's not linear. So this is not zero order. Done. Not zero order. Let's look at the next graph we produce. We're putting natural log on the y-axis. That looks pretty straight to me, right? Looking good. I like this one. This one is straight. Okay, it's looking good, but let's just check the other one. The last graph here, oh, definitely no, that's not a straight line. So second order is out. Okay, so the one that produces the straight line, you look at what is on the y-axis. This one says natural log, so I know that this is first order. And to help you guys remember the order of the y-axis, put them in alphabetical order. 0th order has concentration, starts with a C. First order has natural log, starts with an N. Second order has reciprocal on that y-axis, R. And so in alphabetical order, C, N, R, concentration, natural log, reciprocal, 0, first, second order. That's how you can help yourself remember which graph is which. So this is first order with respect to the hydrogen peroxide. Okay, so part A here, and you're writing your responses on your paper. You just label your paper examples. So this is first order with respect to hydrogen peroxide. Then it says justify your answer. When they say justify, they mean what evidence, what data is presented to you that tells you the answer. Well, the data and evidence presented to us are the graphs. I know that this is first order because of the graph, but I need to be a little bit more specific. I can't just say because the graph. That doesn't mean anything. Because the graph of natural log of the concentration of hydrogen peroxide versus time is a straight line with a constant slope. Okay, so there you go. I answered the question. It's first order. How do I know it's first order? The graph of the natural log versus time is straight, has a constant slope. Part B, write the rate law. The rate law is what we know. This is what we learned last week. Rate equals baby K times the concentration of that reactant raised to its order. This is first order. So I guess technically you could put the 1 if you want to, but I'm not going to because it is understood to be a 1 if there's no number. Okay, that's not bad. Okay, so I know it's first order. I can write the rate law from that. The exponent is 1. Great. Now, part C. What is the value of the rate constant? Specify the units. Rate constant is K, baby K. So baby K equals slope. We're going to take the absolute value of the slope. Slope is rise over run. So I want the slope of that straight line. Use the data to help you. Okay, so at the very top of the paper is that data table. I'm going to just pick 2 points from the data table and I can do my slope. It shouldn't matter which 2 points you pick because the slope is constant, so it shouldn't matter what 2 points you pick. But we might get slight variations because we are dealing with experimental data, which isn't always perfect. So I'm just going to go up here. Sorry if I'm moving too fast there, but I will go back down in just a little bit. This is what I need you now to do. Because we are first order, I just need to look at 2 columns. I now just need to look at the natural log column and the time column because that's what's on our graph. And to calculate the slope, just pick 2 of the data points. And so I'm just going to pick the first 2. I'm going to say, hey, this first time, that's going to be my x1. The second time is my x2. And this over here, y1, y2. You're calculating rise over run. y2 minus y1 over x2 minus x1. Okay, and so that's what we're going to do here. Slope will be equal to y2 minus y1 over x2 minus x1. And again, it doesn't matter which 2 that you pick, but I'm picking those 2. Okay, so for my calculation, we're going to get negative 0.0943 minus 0 over 120 minus 0. Remembering, we are taking the absolute value of our answers. Okay, so 0.0943 divided by 120. I get 7.85 sig figs. We'll go with 3. 7.86 times 10 to the negative 4. That's my numerical answer for K. With K, we always ask for units, right? So I need to write the appropriate units for K. This is first order, looking at our rate law. First order overall. So my shortcut is 1 over molarity raised to the power of overall minus 1. So it's just going to be 1 minus 1, that's 0, so it's not there. So it's just going to be 1 over time, which is going to be, what are we in, seconds? Seconds. So 1 over S. So now for part D, writing the integrated rate law. Integrated rate law means y equals mx plus b. Y equals mx plus b. That's what I need you to think. And so we're just going to substitute in what we have on the y-axis, substitute in our k. Well, no, we don't even have to substitute in our k yet. Let's just hold off on that. Substitute in what we have for b, etc. All right, so here we go. So on our y-axis for first order, we have natural log of the concentration of our reactant. That will be equal to negative k. X-axis is time, so lowercase t, plus the natural log of hydrogen peroxide at time 0. Oh shoot, and I forgot the T again, the baby T down there. That's your integrated rate law. It looks identical to your notes. The only thing different is we actually plug in the chemical formula for the reactant. That's all that's different. Okay. This is your integrated rate law. Now for part E. They want us to calculate the concentration of the hydrogen peroxide at 4,000 seconds. So this is where the integrated rate law comes into play, because I told you, integrated rate law is for problems where they give you time and they ask you to solve for concentration, or vice versa. They give you concentration and they ask you to solve for time. And so what we're going to do here is we're going to take our integrated rate law and we're going to substitute in the numbers. Okay, so we're going to take this answer from part D. And I'm actually going to sub in the time. I'm going to sub in the K. I'm going to sub in our y-intercept. And so natural log of the hydrogen peroxide at time of 4,000 seconds is equal to negative. Grab your answer for K, 7.86 times 10 to the negative 4. Substitute in the desired time, 4,000, and then sub in the natural log of the concentration at time 0, the initial. And so you actually have that number given to you in the data table. I already did the calculation for you. If you were to scroll up to your data table, you'll see the first thing underneath the natural log at time 0. Natural log of the concentration is 0. So I'm very briefly, I will scroll up, I'll show you right here. At time 0, the natural log is 0 for this reaction. So the 0 is what I'm plugging in for the natural log of 0. Natural log at time 0. Okay, so plus 0. I'm going to clean up the right-hand side here. So that will be 7.86 E negative 4 times 4,000. I get negative 3.144. All of that is still equal to the natural log of hydrogen peroxide at time 4,000. All right, we're almost there. They don't want the answer for natural log of concentration. They want the answer for concentration. So those of you who are familiar with logs, you might be able to help us out here. What is the base of natural log? Yeah. That's right. E. Natural log has base E. So the concentration at time 4,000 will be equal to E raised to the power of negative 3.144. And so you need to type this into your calculator. Your E button, if you're using a TI graphing calculator, it's second ln. Okay, so I'll show you where it is on the TI. So I'm going to hit second ln, and it will bring up the E. This is not the same E that we use for scientific notation. E raised to the power of negative 3.144. Enter. I get 0.0431 as the answer. So the concentration is equal to 0.0431. That is the concentration at time 4,000. Concentration is square brackets, which is capital M for molarity. So I have just used the integrated rate law to calculate the concentration of our reactant at 4,000 seconds after the reaction has started.